So let's start off with the solution itself. So we were approached by the European Hockey Federation, and they were doing a project, and for this project they wanted to have an automated camera solution, which is basically for both analysis for sports clubs, hockey clubs, field hockey clubs, and also for entertainment purposes. So just to have a live stream where people can watch. Right now, people often need volunteers, lots of them, and instead, if you have this automated, you do not need these volunteers. And in general, this is a trend in the sports industry. Entertainment and analysis, that's the main point. We want to build a solution which is useful for both entertainment and analysis. Requirements. First, the setup. So what we have is we have two static cameras on the midline of the field, on the pitch, and these film one half of a hockey pitch each. We try to detect some players and the ball there. We apply some rules and some decision making, and then in the end we send commands to a PTZ-camera, which is a pan-tilt zoom camera, so it's automated, and then it should follow the flow of the game very nicely. What is important to note here is that we have everything on-premise for now. So the static cameras are on-premise, the PTZ camera is of course also on-premise because it has to film the pitch, but also there's a local server, because if you're talking about, for example, full HD images that we want to send in 25 frames per second, we're talking about like 150 megabytes per second that we have to send per camera. So if you want to do this somewhere in Germany or Belgium or in Spain where the internet is very crappy as is, we also want to have a live stream, we really cannot do this over 3 or 2 or 1G or the Wi-Fi. So that's why we chose to have a local server there. It's also for latency purposes in general, which is of course very important. If we are talking about, we have this static camera, it processes the input and then we have to send command to the PTZ camera. We're talking about like a maximum of 300 milliseconds delay, which we would really like, because otherwise you're always lagging behind the flow of the game. And of course the accuracy is important, and there's always this interplay between these things, because if we have a very powerful model to always be able to detect the ball, then the model itself will already have such a high latency, or we need to buy such expensive GPUs or graphic cards that we really cannot have a sellable system, so to say. Keep those things in mind, because the latency is very important later on in the talk as well. So I'll talk about the architecture. I already mentioned a second ago that we have these static cameras as input. So we have an image. It flows into our input and pre-processing step. Then we do some decision making. So in the input and pre-processing step, we actually detect the players and the ball. At least we would like to always detect the players and the ball. And then in the decision making, we have to deal with it, because sometimes you do not detect the ball, and then we have to rely on the player detections to actually send the commands. And afterwards, we decide, well, the camera should go here, at least on the field it should go, for example, to the goal on the left. And then we have to translate this into an actual command for the camera, which is on the camera control. I will go a bit deeper into each of these parts. So for the input, we have the static camera as input. We use OpenCV video capture to get these. And then we do some light pre-processing, so we mainly crop and resize the images. We have experimented before also by using like a different color scheme, because it makes it sometimes easier to detect the ball, because the ball is white, the field, the pitch here is green, and the ball can easily get lost in the pitch. So we've experimented with, for example, different, not RGB values, but different values, and that sometimes makes it easier to detect the ball. That would also be done in the pre-processing. We also use OpenCV for that. Then we have a queue, so we put all these images into a queue. We use PyData for that. I will get into that a bit later, because we first tried it with multiprocessing queues and we ran into a bunch of problems. And afterwards, we have these pre-processed images. We're ready to do the detections. We use the YOLO models for this. And we also have an OpenCV implementation. The frames are then aggregated, so all this information is aggregated because we have two of the cameras and we want both cameras as inputs. So we have, well, maybe we detect the ball left but not right, but we detect players on both sides of the pitch usually. So we have to aggregate those. And then we're ready for the next step. So now we have the player and ball detections as accurate as we hope, as we like. And these go into the decision maker. So the decision maker basically does 3 steps. We produce some second-hand events. So for example, instead of just having the player coordinates, we want to know how many players are in the penalty area, like the circle. I'm not a hockey player myself, but and how many are more on the midfield and stuff like that. But also here we may run some, no actually those are the features. And we use those features in the event producers. So for the features we mostly use just Python and maybe some NumPy. And then we want to detect some events. So for example the ball, we identify that as an event because later on in the rules we say if we detect the ball we generally just want to focus on or near the ball. However, for hockey, for field hockey, you have these penalty corners. And what happens when you just use like the ball and the players for detections, we see the ball, then when they're taking a penalty corner, the ball is laid on this white line, so you lose it, like there's no way to see it. And then we have to use the player detections. And in general, we just say, well, if we have all the players, we just aim somewhere in the middle of those players. But if there's a penalty corner, you're then just filming the midline. Because in general, there are like 5 or 10 players who are all standing in one blob on the penalty corner area. So the YOLO models do not work very well. Then you have 5 very clearly, or 7 or 10 very clear players on the midfield. So you see like 10 players here, 5 players there, and it just films these players on the midfield. I do not have an image, I forgot to include it, but it's quite funny actually. So we have to detect these penalty corners. So we just use some machine learning models for that, maybe sklearn, and then we can actually aim the camera at the penalty corner area. Once we've done that, we have this, we say, well, you have to aim this part of the field. So then it goes into the camera controller. In the example that I said before, we use one PTZ camera, but we have a testing setup where we actually have 3. So also on the other sides of the pitch. So we have you can use that for more camera angles, which is for both analysis and entertainment, of course, nice. So we have to translate per camera the field coordinates to an actual camera command, which is basically like a lat long. And we also have to do some speed or zoom computation, and we use AstroPy and NumPy for that. And then via the OnViv protocol, we send the actual command to the camera. As I said before, latency is important. So what we wanted to do from the very start is to monitor this, but also for like the total latency and for each of the different tasks that I just mentioned, like the features producing, the decision making, everything. So we need to monitor this because if we just run the application, we have no idea if it's fast or why it's not working basically, because always there's something which makes it not work. And we need to monitor some of the performance. So that's basically like how many players and how often do we detect the ball. We do that mostly separately, just when we're training the models. And total running time. And most importantly, we need to do this somewhat automatically, or actually fully automatically, because if we have to read through all the logs every time, it just doesn't work. Because then, we tried this in the beginning, and we said, well, it works very fine. I see a 100 millisecond delay. We're doing great. Let's just continue. And then once we implemented the logging, we actually saw, well, that's really not what's happening if you let the application run for 50 minutes or for 30 minutes. So there's some importance about the automatic part here. Well, how to do logging in Python? If you've programmed in Python before, you probably use the native logging module somewhere, but there are many packages here. So we set up a list of requirements. So first, we should be able to write lines to a file. That's like the most basic part of logging. So we have a logger, we define a file path that we have to log to, and then every time that we have a new event, we write to the file path as a string the message. Now, next, what we want to do is we need to be able to automatically parse these. So we actually want to make it in a format that's not just like text-based, because then we have to parse all these text, and it's just not very nice. So what we can do is we can just JSONify this message and just say, well, we'll make it into some sort of dictionary or JSON object, which we can then read very easily. So instead of just building it as a string, we dump it. And important to note here is that basically we end up with a file where each line is a JSON object, which we can then very easily parse. The next point here is that if you've worked with JSON before, you know that many of the objects that are in Python cannot actually be outputted to JSON. So we have to encode these. So we built oh, I'm missing. Yeah, we built like a JSON encoder which does this job for us. So for example, the datetime is easily formatted into a certain string formatting, numpy arrays as well, and the window is one of our own classes, which is like a frame where we have all these player coordinates. So we have to be able to parse that as well. Then this part is the same, but instead of just saying, okay, we log the message as is, for each of the values in this object, in the dictionary object, it applies the class above. And lastly, it should be non-blocking. We do not want the full application to run into some error because the logging module is actually not working. So what we do is we just start a different process for it, and then we have in a separate process, we log all these things. So basically when somewhere in the application we say we want to log something, we will just put it into a queue, and then the logger, the data logger, will work. So these are like the 4 requirements, and during the setting of thinking or conceptualizing these requirements, we already wrote most of the code. So we could say, well, we can use one of those packages, but actually we've already pretty much built it ourselves. So this is also something that we noticed. You can use packages, generally it's good, but if it's very simple, you can maybe just make it yourself. Is it the only way to do this? No, of course not. Is it the best way? I don't know, but it was easy to implement and it's working fine for us. So how do we use it? This is another code snippet that I'll just go through very quickly. This is like the decision maker that I talked about before. So we have the input, decision maker, and then the camera control. So for the input, we do several steps. We have like an estimator which estimates where the area of interest is based on all the player coordinates. We have some feature producers, as I just said, event producers, decision rules. The last 2 are not really important. And basically the decision maker just computes, it calculates where the camera should be aimed at. So we do that here. First we generate an intermediate ID, which we can then use to compute the total running time for the decision maker from start to end. And we log that it started, so then we have the first time we actually have this ID. And here, for example, we compute this area of interest, and we also log this. So it logs the event, logs the ID, it logs some attributes, and basically this is done. This is an example of the output. I reformatted it a little bit, and I threw some things out so it doesn't overwhelm you, but it may still overwhelm. But here we can actually see this event. So we have the decision maker which started, we have the area of interest which was determined, and then we have all these attributes that we actually store here. What's also interesting, I like this part because here we have the attributes, we have the ball. So this is actually the field coordinate of the ball. So we say the absolute center is 0, 0. So it's like a bit to the right and a bit downwards. That's where the ball was actually at. And we can actually also see that here in one of our earlier log events, that the YOLO model actually actually identifies or detects this ball here. It's a fun part, I think. And then we have some other events, but this is not really important. One thing that is important is the input ID, as I talked about before. We want to monitor the full latency of the model. So we have to know when did an image come in, which image was it, and how is it used throughout the process. So somewhere before this, we actually make this, for example, this input ID. And then we say, well, this input ID, so from this camera, at this timestamp, we generated a frame, or a frame came into our application. And then we use specifically this frame ID in this step. And that way we actually also know when this frame ID was used last, which is somewhere below here. And if you just compute like the timestamps between those, you have the full latency of the model, of the full application actually. So how do we then use this? This is like the frame lifetime as I discussed before. And I mentioned at the beginning that we should have around 300 millisecond latency. And what you can see here is that completely failed during our first attempts because, well, in general it's around like 1 second, which is not even that bad. But for some reason there's this weird tail at the end where the frame that we produce takes up to 8 seconds to be actually used in a camera command. And that's not really something you want, because then you get this situation where we very nicely detect the ball and the camera goes there, but by the time that we actually are there, the ball has been already like very far away. So Then we went about debugging this. So the next step is to, what we did is check this frame lifetime over the time that the application has been running. What we also see here is that it's, for some reason, it is building up. So the longer the application ran, the longer it took between the very start of a frame and between when we actually use it in our application. And this is quite weird. And what we noticed is that the multiprocessing queue, which many people use, actually has a bottleneck of having like a limited size in the queue itself. So here's a code snippet of how we basically use this multiprocessing queue. So we have the input part. So in the input part, we put these frames into a queue. And then we have the output part where we actually get them out of the queue. And the problem is we are putting frames at a higher rate into the queue than out of the queue. So to solve this, because and we want to use the last frame every time. So at the outputs, we keep pulling things out of the queue until the queue is empty, which is like right here. We have this try except block. So once the queue is empty, we stop pulling things out of the queue and we start actually doing the detections. However, what we noticed is that in this multiprocessing queue, things do not actually get put in the queue unless there's room in a queue. So what we end up having is a situation where we are putting 10 frames per second into the queue, but then in fact they end up somewhere before the queue, and only after a while they are put into the queue. And then we get this except statement every time because there's only one thing in the queue. It's a bit of a complicated story, but the result was that we were using over time older and older and older frames. So while the other parts of the application were running quite nicely, we were just always using old data. So how did we solve this? We use a different type of queue, and we actually tested before, of course, if this queue would be working, and it was. I won't go into the details of this code, but it's basically ZMQ, 0MQ, is also a Python package which is able to handle larger amounts of data more easily. And it works slightly differently, but still you have like this thing, like a publisher, which puts things into the queue, and then we have a subscriber which takes things from the queue and uses it in the rest of the application. So afterwards, this wasn't very early on in our process, so we didn't even have a graphics card yet, so the times are still too high, as you can see, but at least they weren't building up over time. So now they're nicely around 1 second. There are some exceptions, but it's not as in the image I showed before, that it actually builds up to like 8 seconds at the end of the application runtime. And lastly, what we can also do with this information is actually plot the latency per event. So each event is one of those steps that I talked about before, like the decision maker, which produces features and stuff like that. And here you can see that many of the events that we have actually work very fast. They've like I don't know, like a 0.2 millisecond delay, and we should focus on the parts which have a high delay. So here it's actually a part of the camera where we ask it where the position is, so where it's currently at, because we send like a command, well, you have to move that way, but while it's moving that way, we are already sending the new command, but we have to know where it is to know which speed it needs, which velocity it needs for the other part. So we actually ask that, we ask where are you currently at, and we show here that that's right now really a bottleneck, which is also a problem, and we're working on fixing that. That was basically what I wanted to say. If you have any questions, please ask.
Thanks. Any questions?
Remark. The problem you solve with your image buffer is, I think, already part of OpenCV. So I think OpenCV has an internal buffer. When you do a read, you always get the last image.
You mean in the video capture? So so the problem is not really there. The buffer there works perfectly fine. But then after pre-processing the image, we put it into a new queue until the YOLO models are basically ready to detect something else.
Why should you?
Because the YOLO models do not run in sync with the video capture. We cannot get the YOLO models to work at 25 frames per second.
But when you have the trio, so when you get the last new image, when
Yes.
you are ready with processing, you have the most recent one. So why?
You have to throw those previous images away somehow.
Don't when you do a read,
Yes.
you get the last new one.
I get what you're saying. So you're saying Yeah, if you have those in a combined sense, then it works. But we have to. We wanted to ensure that we can also use this for other purposes. And in that case, we may deal with different input sources. So we wanted to decouple the input, so for example, the camera source, from the detections. So there's a deep coupling point there, programmatically, and that's why we put like something in between. And we just use the queues before that because we've worked with them often and they never not work.
Use with events then.
What do you mean?
Send events from the image processing is ready, send an event to the buffer or to your camera controller and get the latest one.
Ik would of yeah, it's not. I'm not trying to discuss whether it's of course possible. I think. In the back, yes.
Do you process every single frame?
Yeah, we do right now.
Why not dropping some?
Yeah, because then you still have to. Then we would have in the detection, like in the detectors, we would have to say, well, we're ready. So now only process the next frame. So we have like a feedback loop. So that's why for now we decided to just process every single frame because the resizing and cropping is not really something that's building up a lot of latency.
And you said that, well, I mean, you already fixed the queue issues, that's nice. But you said that you would need 25 FPS in the YOLO. And what processor are you using for that?
Yeah, just to be clear. So what I meant is that if we have the YOLO at 25 FPS, then you do not need a queue in between because we can just count YOLO as like a pre-processing step. And you can just put it right there. Even then, there are some things to keep in mind. But if it's not, so if it's lower than that, then that's why we built a queue in between. But your question is more like which YOLO model we're using, or?
No, more like which hardware are you using to run YOLO?
We have. I do not know the CPU model or type, but for the GPU we have a RTX 3080, 3060 or 3080, 3060 I think.
Oh, so you do have a GPU?
Yeah, we do have a GPU right now. And the example, like the latencies that I showed before, with the like 1 second, we didn't have one yet, but we've used one because 1 second is just too high, so we really needed one.
Have you considered quantizing the
We have not yet.
because that would also remove a point from your processing power.
Okay. It's something to look into. One thing to keep in mind is that we have to run these for each camera, and also we run separate models for the ball and the player because we noticed that when we try to encapsulate them in one model, the performance for the ball really dropped because the difference between a foot and a ball is apparently very difficult to detect for YOLO. Not yet. So we have currently one test set up in Belgium. We have been, which was at European Championships in Amsterdam last June, which was also the first time that we experimented with the actually computer vision. Before that, the players were trackers. And there the setup was also a bit differently because we partnered with the 5G up here. And we actually used a 5G connection instead of a local server. But there's currently Phil being implemented in England, and there should be a couple being implemented in the upcoming month in Germany as well. So we're also looking into even more predictionalizing this and having it run simultaneously on multiple fields.
Yeah, and do you have to retrain your models from this location, or is it working fine?
I'm sorry, I didn't quite catch that.
If you use new location, you have to retrain models.
Yes, definitely. Especially if the distance from camera to field is similar and also the pitch color is similar, the models work all right. And the player models generally work all right regardless of which field it is. But if the pitch colors change, so you have also these blue fields in hockey, we really noticed the performance for the ball dropping. And also if the camera is a lot further away, it didn't seem to actually be able to catch the ball. So we had to retrain quite a few times already.
Losing the ball. Have you considered using some kind of predictive filter, like a Kalman filter?
Yeah, well, I think we have considered it, and I think we will be implementing that as well. But we had to actually up the accuracy for the ball detector anyways before even considering a Kalman filter, because before if you have it like once every 3 detections, the Kalman filter doesn't really work. You actually have to have it in successive frames. But it is something that will be interesting to see. I'm from Idle, which is very tinily written on my thing here. Idle is a company by two entities. So my own company, Whitebox Data Science, which I do together with Koen, who is actually sitting there, and also by Team TV. And there's also someone from Team TV sitting here, coincidentally, also called Koen. So that's a bit confusing. And we set up this entity together. Well, not per se sports. There are other companies which are doing this.
In hockey as well.
Also, yes. But the main difference between those companies and ours is that they use a system where they have like 4 static cameras on the midline, which each film like a different part of the pitch, and then they stitch those digitally together. And well, you have some advantages because it's generally a bit faster because you do not have to actually send the PTZ commands. We believe that our system will be better because we can actually zoom as well without losing any of the resolution and stuff like that, or having to do difficult tricks there.
And I can imagine in football having so much money, there are just cameramen everywhere.
Yeah, so indeed, this is more a business point of view, but from the business point of view, indeed, it's we target like the top segments for example, field hockey, but the top segments for soccer, for football, are not really interesting right now because, well, they have so much money. Why would they need an automated camera system? And I think before we actually have something that works better than a human cameraman will be a while or never.
Any other question? We have a few minutes here, so I would like to ask you a question.
Mhm.
Is your decision-making function supported just to one camera, the combination of one camera, or multiple cameras, or it can also have multiple cameras taking the picture from the frame from different points of view?
So if I understand correctly, the question is whether the decision making is for a single camera or for multiple cameras. Yeah, so the decision making is for all cameras at the same time. So it basically determines where the interesting point is on the field. And then in the camera controller, I didn't show it here, but in the camera controller we can also identify or use rules per camera. So for example, what we noticed is that if we just use the field coordinate as is, if the ball or the players are somewhere like far away from the camera, it is really tilted up very high because it tries to have the ball or the players in the middle of the camera, but then you have like a very large amount of sky that you see. So we experimented with tilting it downwards, and that's of course different per camera. Because, yeah.
Thanks. Any other question?
So you mentioned events of corners, right, in the game.
Mm-hmm.
Have you tried detecting any other events, like a goal, for example?
Well, what we did beforehand, I talked about like they had these trackers, so we didn't. I can't touch that, of course. We had these trackers instead of using like computer vision to detect players, and we didn't have the ball yet, so we tried to do it just by having those players. And what we noticed there is that the middle of the players is generally all right, except in 2 situations where they're moving very fast, like a counter attack, or during like the build-up phase, so when they're just passing around at the back. So we tried to build models to detect that at some point, which they were working all right, I think. But once we could actually detect the ball, that's of course a way better approximation for the interesting point of the field.
So I imagine, like, if you play hockey on an amateur level, I mean, you pay quite some good money to have a highlight reel of your game you just played, right?
Well, this is that's a different application, but we're also working on that for tennis right now. So we're trying to detect events for tennis, like the forehand, the backhand, stuff like that. But we also want to implement this in other sports as well. So for hockey, indeed, if you can detect a goal in a penalty corner and like a quick attack with a shot, then it's already a very interesting product, I think. But I think that will be a separate application because it will be a separate application because it's not really necessary to do that real time.
Sure, exactly.
Yeah.